welcome everybody to a joint seminar of the Harvard-China Project on Energy, Economy, and Environment and the Lakshmi Mittal and Family South Asia Institute. My name is Chris Nielsen. I'm the executive director of the first program, the China Project. And in a moment, I'm going to pass this over to my counterpart in the Mittal Institute, Hitesh Hathi, to introduce our speaker today, Professor McElroy. But because this is the first time these two programs have partnered on anything, and we're going to have an audience that is drawn from two different communities, very distinct communities, I want to take a couple of minutes just to help everybody get a little bit clearer about what these two programs do. They both have international collaborative objectives, but also they both have interdisciplinary cross-Harvard ones. In the case of the China Project, we research climate change and air pollution problems, but from a variety of disciplinary and topical perspectives. And we do most of our research in collaboration with partners in China who are almost all drawn from our network of more than 200 alumni, research alumni that are in China. We're based in the sciences. We're in the Paulson School of Engineering and Applied Sciences. And so we do atmospheric chemistry, we do some applications in climate science, we do a lot of different kinds of energy science, but we're also very active in economics. We've got a longstanding economics program, environmental health, urban planning, and other fields over time. And policy is sort of in the background of almost everything that we do. The Mittal Institute, and I don't really represent it. I'm basically borrowing from their mission statement, but Hitesh can elaborate if he wants. The Mittal Institute engages through interdisciplinary research to advance understanding of critical issues related to South Asia and its relationship with the world. It facilitates scholarly exchanges of students, faculty, visiting scholars, and public figures. It sponsors lectures and conferences. It supports students with grants for language, research, and internships. It offers faculty research grants to bring knowledge from South Asia to Harvard. And it's basically engaged in building a community of stakeholders committed to scholarship on South Asia. So a few housekeeping issues before I turn it over to Hitesh. This talk is being recorded and will be posted online, so keep that in mind. Secondly, we like to make these seminars, these online seminars, as close to an in-person seminar as possible. And what we mean by that is that when we get to the Q&A period, you'll be allowed to ask your question directly to Professor McElroy. To do this, you'll need to raise your hand digitally, which is a function, as probably most of you know, in Zoom. It's usually in the reactions menu at the bottom of your screen. You raise your hand and we'll call on you to ask your question, but and you'll have to unmute yourself. So the point here is that everybody's microphone is actually live, and so if you're not talking, if you haven't been invited to say something, you need to make sure you're on mute and wait until you're asked to ask a question. So Hitesh, up to you, on to you.
Chris, thank you. And I have to say, I'm actually relatively new at the Mittal. I'm in my third month now, and there's nothing more bracing and maybe more useful than having one's own mission statement read to one in a public forum. But I can tell you, we are actually living up to it. So thank you. For those of you who don't know, the Mittal Institute is focused on South Asia. Climate change is one of the things, energy, climate change, economy. It's an area that we have become more and more interested in and are starting a project on that. And so I'm very happy to be part of this conversation, to be in collaboration with your group. And I want to say I was very touched, you know, when Kelly called to ask me if I would introduce Professor McElroy. I was very touched. First of all, you know, there's no more urgent topic before any of us today in the world. In India and China, with fast growing economies and about 2.5 billion people between them, and if you include all of South Asia, it's an even larger population. a lot of what will happen to the world will be decided by what happens in South Asia and East Asia. So there's nothing more urgent. So both in terms of topic, but Professor McElroy, I should say, he and I have had a relationship for 25 years that he doesn't know about, which I'm about to tell him. Which is when I was and I'll give you, as you all know, he's the chair of the Harvard China Project on Energy, Economy, and Environment. He founded that project in 1993. When I was a graduate student in Harvard and an acting resident dean, I had students who used to come and tell me all about him. They were very excited because he, of course, was one of the people who was a pioneer at Harvard in founding a study of the environment, and that was something that was comprehensive and included the sciences, but other fields also. He has been the director of the Center for Earth and Planetary Physics. He was the founding director of the University Center for the Environment, founding chair of the Department of Earth and Planetary Sciences. He has a large number of books and articles, a forthcoming book, actually, that's on India's climate and energy landscape. So I had heard about him through students. And then I was teaching at Harvard and I happened to be hosting, and Mike, I don't know if you'll remember this, I happened to be hosting the Speaker of the Indian Parliament. And she was here for 3 days, partly on an official visit, partly on a personal visit. I don't know how I became the host. On the first morning, I said, so what would you like to do? Whom would you like to meet? And she said, and this is the reason I actually always had trouble saying your name. She said, I want to meet Professor McElroy. And I said, of all the professors, you want to meet him? I thought she would say Amartya Sen. She said, yes, yes, yes. Every government official in India knows he's Al Gore's eco-brain. And I want to know what he knows so we can be doing some of it. So I actually introduced the two of them. They had a fantastic hour-and-a-half long conversation in your office. I was just on the side. A year or two later, I happened to be hosting a very senior Pakistani government official whom I won't name for complicated reasons. And I asked him whom he wanted to meet beyond the people that were already on his schedule. And he wanted to meet Professor Michael McElroy because he said, what we've heard in Pakistan is no one knows more about the environment than he does, and we need to talk to him to figure out what we should be doing to save ourselves. So, so there were two public officials from South Asia, essentially at the top of their field, both of whom I introduced to Professor McElroy. Some years later, I happened to be working for National Public Radio. I had just started. It was a national program. I was an editor, but the youngest, junior most editor. And we had one of those serious meetings where we were deciding how we would cover the environment. And it was one of those meetings where we decided, for example, that the other side was no longer going to get equal billing, sort of, oh, there's this and there's that. I don't know if you all remember, some of you may not be old enough, but there was a moment into the 90s and early 2000s when you talked about the environment, you had to say, but some people think, nothing is happening. And that's when we gave it up. But at the end of that discussion, we were building up a list of who are the sterling experts whom we can rely on. And of course, Michael McElroy was again at the top of that list. So in 3 different roles, in 3 different functions, he's been a part of sort of my professional life. And here I am back 20 some years later at Harvard. And one of my first acts is to introduce you. It's a great honor. I want to say that you really have been a pioneer in these fields and also in linking the science, the energy, and the economic ideas with the environmental concerns we have. Looking forward to hearing what you have to say. So I'll stop now and let you go on.
Thank you so much, Hadesh. I do now remember those events that are almost 20 years ago, and you've been a real hero in terms of bringing India, and in that case Pakistan, into the Harvard community, and I'm looking forward really to working with you in your new role. And so the other thing I will just comment on, you're overly generous, I have to say. But anyway, it's a real pleasure to have you back at Harvard and to be able to interact with you in this occasion and in the future. So what I want to do is let me just sort of make a few brief comments before I begin my formal presentation. So as Hitesh mentioned, we began this work on understanding China's environment in particular, over 20 some years ago. And the reason we did that at the time was that China was obviously a rapidly growing economy, a rapidly growing population, serious environmental issues. And I had the good fortune to have a good relationship with Al Gore, who had just become the vice president. And Al Gore introduced us to some senior Chinese officials, and we had very high level policy operations in China, the opportunity to meet with the Chinese premiers, and to serve on a council called the China Council for International Cooperation on Environment that brought equal numbers of foreigners and Chinese experts together for 3 days every year to talk about serious issues. So what is pretty clear at this stage of the game, and you certainly appreciate that, is that India is in some respects, in terms of thinking about the environment, maybe where China was in 1992 or 1993. India is a rapidly growing economy. I'll talk more about that, a rapidly growing environmental issue, energy problems, and that's sort of the background for why it's really, really important for us to have this focus, not just on China, but on India. And indeed, what Chris and I have been talking about with Kelly as well is, I think we need to broaden our scope from the China project to essentially an Asia-wide series of focus, both sides. And I'm very pleased to see my friend Jim Anderson here, who has been thinking about, has been building a sort of amazing opportunity to observe things from a plane that's going to fly in the stratosphere. And Jim is interested in working hard on understanding the stability of the ice in Tibet, which obviously has a big important role to play in China, as well as in India and other downstream areas. So thanks, Jim, for taking the time to join us. Okay, so what I want to do, give you a little bit of I want to begin by talking a little bit about the context of what the climate issue really is at this point in time. And then I want to pay special attention to India to understand exactly what the background is for India. How has India changed between 2000 and let's say 2019? And then I'm going to talk a little bit about the Indian Prime Minister's commitments under the Paris and the Glasgow agreements. And then I'm going to talk about some of our specific work here, including two papers really that I'll give you a little bit of background. And then I want to come back and talk a little bit about some of the other issues that clearly are of concern for India, including air quality issues and implications for climate and society, and in fact for something that I've learned from my good friend Prem, the fact that we have to have a really serious concern about poverty alleviation and specific issues that really are important for India, this rapidly growing country. So that's sort of my background. And now if we go to the first slide. Okay, that's just the title. Let's go to the next slide. So this is I think a really important figure that gives you the best estimate of what has happened to the global average temperature from 1880 essentially up to 2020, up to the latest time I could find this. And this is a really interesting figure. It includes the global average temperature, ocean and land. And as you see here, the global average surface temperature is now about 1 degree or so warmer than what it was in the pre-industrial period, to the left of that particular figure. And I'm going to sort of just mention briefly here the fact that the IPCC in its more recent publications has made the point that if we're going to avoid really catastrophic climate issues in the near future, we need to make sure that this global average surface temperature doesn't get higher than 1.5 degrees. And look where we are at the moment. We're essentially a little bit above 1 degree. So we're very close to a very serious issue. I also want to sort of mention here the fact what you see in this chart is essentially 3 phases. To the left, you see the temperature beginning to rise from 1900 to 1940. And then you see the temperature go sort of relatively flat up to about 1970. And since then, we're on a record-breaking rise, and no sign of that rise ending. I will make the argument and come back to it in the India context that the hiatus that you see here, I believe is due to not just the CO2 and the greenhouse gases, which are responsible for the overall rise, but in fact, sulfate aerosols produced by burning coal produces these aerosols that are interacting with clouds and reflecting sunlight and essentially offsetting the warming that you get from the greenhouse gases. And I will come back to this issue in the India context a little later on. You might ask, why is it that that this trend ended? And the reason the trend ended is that it was largely due to emissions from North America and Europe. And in the early days, those emissions were almost entirely due to dirty coal in the 1940s on. And people died, a large number of people died from an air quality issue in London in 1950. And people died in Denora, Pennsylvania from another issue. And so there was a general public concern about this. And so how do you deal with the problem? They didn't deal with the problem by stopping using coal. What they did was that in the British sense in particular, the decision was to in fact switch from dirty coal to clean coal, so-called smokeless fuel. And it was only when people later on became concerned about acid rain in the United States and in Europe that steps were taken to eliminate or cut down on the sulfur emissions, and that led to the end of this hiatus. In other words, in Europe and in the United States, the sulfate aerosol was no longer the controlling influence. The greenhouse gases were really running the show. But at the same time, we were watching a growth in the use of coal in China and to a lesser extent in India. And we were looking at air quality issues, the same sort of issues. And I'll come back and talk about this in the India context as I get closer to the end. Next slide. That previous slide was the global average surface temperature. This is a slide that breaks it out between the land surface and the sea surface. And you see here, the land surface is actually rising more rapidly than the sea is. And there's a difference between the land and the sea surface temperatures. And the reason I want to sort of mention this is that the land-sea temperature contrast is very, very important for so-called monsoonal circulations. And so if we're interested in the stability of the Indian monsoon, which is so critically important for agriculture and for the lives of people, we need to be very careful about whether the land-sea surface temperature is changing and what the implications of that might be for climate in regions that are affected by this monsoonal circulation. That's not just India. It also includes parts of Africa, and it includes parts of East Asia and China in particular. So next slide. To put India in context, this is a chart showing the growth in emissions of CO2, the primary greenhouse gas, the primary concern that we have, the growth of those emissions going back to 1960 for the 6 largest emitters. And what stands out here is the rapid rise of the emissions from China beginning in 2000, let's say, and China in the early 2000s becomes a larger emitter than the United States. The United States is sort of relatively flat up here to 2019 in this particular chart. And the European Union is interesting because it's been flat to down over the years back to 1990. And now you sort of look at India and you see this sort of steady rise in India to the point where in terms of national emissions, India is number 3. If you count the European Union as 1, India is number 4. But if you look at the rise is strikingly large. And so what happens in the future is of great concern for what we're trying to do with India. Next chart. So this is a chart that is from the IEA, International Energy Agency, that is a very good summary of recent events in India. So you see from 2000 to 2019, the growth in population. So India is poised to become the most populous country in the world, surpassing China. GDP is interesting also. GDP has been rising from 2000 to 2019. And on the right-hand side, you see the growth in energy demand, and from 2000 to 2019. And what is interesting there is you see the importance of coal in the Indian context. Coal is a major source of energy. Units here are millions of tons of oil equivalent. But in India, as is the case for China, is incredibly dependent on its domestic sources of coal and on imported oil and imported natural gas. And then we have traditional biomass, mostly in the rural areas, and we have a very small but growing contribution from renewables. So next. This chart gives you a breakdown on the CO2 emissions from the Indian energy sector in 2019. And so what you see is the power sector, electricity generation, is the major source of CO2 emissions. And it's mostly from coal-fired power plants. And then for industry, there are 3, industry is not trivial in terms of its contributions to CO2 emissions, but there are sort of 3 sources indicated here. One is iron and steel, a second one is cement, and then there's a whole bunch of others. And so we'll actually have have an opportunity to talk about what we can do about these emissions and not just the power sector. Transportation, complicated in India, where you have trucks, 2 to 3 wheelers and cars, and it's a significant source of CO2 emissions. And then buildings, including residences and commercial buildings, and then agriculture down at the bottom. So this is a useful background to where India is at the moment, essentially where it is in 2019. So next chart. I thought it was good to put the Indian climate commitments up here at this stage of the game. So the commitment is to increase the non-fossil electricity generation capacity to 500 gigawatts by 2030, which would meet 50% of the energy requirements from renewable energy by 2030. Reduce the projected carbon emissions by 1 billion tons from 2021 to 2030. Then to reduce the carbon intensity of the Indian economy by 45% by 2030 relative to 2005. These are pretty ambitious targets, and it isn't clear that they can be met, but it's an important milestone for what Prime Minister Modi is attempting to do. And then finally, the announcement that India proposes to achieve a target of net zero carbon emissions by 2070, comparing that with the US, for example. The US hopes to be carbon neutral by 2050, if not earlier. Europe about the same, and China has talked about 2060. So these are ambitious targets. And if these countries meet these targets, we're looking at a totally different world, a totally different energy world in particular. Okay, next chart. So what I'm now going to do is I'm going to show you some of the results from one of our papers that was published in Nature Communications in 2020. And so what we're going to do here is the point of the calculation that we did was to look at how could you in fact transition to more renewable energy in the case of the Indian energy economy. And more renewable energy in particular is to look at the possibility of having a significant source from solar, PV in particular, and also from wind. And so this is the sort of the ambitious target in this this study that we started. We've had for many years, we've had the ability to use stimulated meteorological data to be able to do a good assessment of what the potential is for wind and solar anywhere in the world. And we've done this extensively in China, and we've done it in other countries, and now we're doing it in the context of India. So the first thing we have to do here is we have to sort of figure out how much electricity can you generate from wind on the left-hand side and solar. And when we do this calculation, what we want to do is to not just consider the possibility of producing wind-generated electricity everywhere in India, and the same thing with solar. We have to recognize that there are constraints. The constraints in the case of wind are actually a little less serious than the constraints in the case of solar. So what we do is we don't want to build a wind farm in a region that is heavily cultivated, or in an urban region, or in a water medium that is critical. In the case of solar, it's a little bit more complicated, because with wind, the beauty of wind is that you build a turbine, you install a turbine, the turbine goes up to a significant altitude and begins to capture the wind that's available there to produce electricity. But the ground print of the turbine is relatively small. So, for example, you can install a turbine in the middle of Iowa in a farmland, and so a lot of the growth of wind in the United States has actually taken place in rural areas, agricultural areas, where the farmer simply rents out the space for the turbine and collects a significant rent just by having the turbine on his land, without it interfering particularly with the way in which he's using that land, whether it's for cropping or for animals. And so that's an important thing. Difference is with solar is that if you're going to install a solar array that is going to provide a significant amount of electricity, you have to use a lot of land. You know, it's not like the turbines sticking up in the air. The PV panels have to occupy a significant amount of land. And so when we do this study, we deliberately exclude certain areas for both wind and, more importantly, for solar. And for solar, we don't want to, in fact, set up a fight between the power generation and the farmers. And so we want to stay away from agricultural areas that are rich agricultural areas when we start building a PV system. But what these two charts are showing you is what, with those constraints, what the potential is for wind and the potential is for solar. And you see 22,000 terawatt hours or so for onshore wind, and 21,000 for solar. And this is way, way higher than the projected demand for electricity in India in 2040, in 2050, or in 2070. So the resource is significantly present. And so that is the beginning of the study that I'm going to summarize. Now, what we did in this particular study was to look at the potential to supply 20%, 40%, 60%, 80% of electricity from renewables in 2040. And we're on the right-hand side, we're going to look at the cost of doing that. And so let me say a few more words about the way in which we do this study. In the India study, this is essentially an economic analysis as well as a scientific analysis. What we're doing is we're looking at 5 regions of India. And we're looking at how those regions are interconnected in the transmission grid. And now we're going to say, okay, we want to minimize the cost of providing, let's say, 80% of electricity for the nation. And what is the optimal way to do that? In other words, this is a model that in fact tries to minimize the cost, considering the cost of the installation of the wind and solar, the cost of operating the continue to operate some fraction of the coal powered system, and also the cost of investing in expansion of the grid from between these 5 regions, and finally also the cost of storage, because one of the problems you have with wind and solar and renewables is the variability. You have to deal with the variability. Now, On the right-hand side of this chart is the estimated of the cost of operating this system in 2040. And what you see is, our conclusion is that you could supply 80% of the electricity that you need in 2040 from renewables at a cost that is actually lower than the cost of delivering the electricity in a sort of business as usual mode. And that's a very important statement. And the other thing you see in this chart is that wind plays a major role, solar plays a major role, and at the 80% level, you're down to a significant reduction in the amount of coal that's being used and in the production of CO2 from the coal. Next chart. Now, this is a sort of a summary of the conclusions from this study, and you can see the regions that we have actually considered: South region, West, North, East, Northeast. And what you see in these circular things is the contribution in this model to the demand for electricity in the 80% case that we want to blow up here. And you can see in on the left of this chart a significant role for wind and a significant role for storage and other opportunities. And the right-hand side, you see that solar is a significant contributor, and the arrows joining these regions represent the interconnection that is exchanging electricity between these different regions, so that you get to that national level that we talked about before. Okay, so let me switch now to another study. This is a study in which, if you look at the assumptions, it's a study of trying to get to zero carbon by 2050. So some of the assumptions in this study that we have been doing, number one is to have 100% electrified residential sector. In other words, that's going to be good for the poor people who are currently using biomass in the rural areas and mostly women, to cook and in fact impacting their public health in a major way because of the fumes and stuff that is going with that. Our assumption is that we also have 100% electrified the commercial sector, hospitals, buildings, office buildings, and so on. The other thing in assumption that we're making in 2050 is that we're going to electrify the short distance road transport, the two-wheelers, three-wheelers, and the cars. And then in the study, we're also going to look at what we can do about the industrial sector that's currently significant, as we saw, a significant source of CO2 in terms of reducing the consumption of fossil fuel in the iron and steel industry, in the cement industry, and some of the other chemical industries that are really important for India. And we're going to do this with a model that has, in fact, use some economic assumptions about the aspirations of India for its power sector, its industrial demand, its population growth, and so on, between now and 2050. And the other thing that I really need to mention here is that in doing these studies that we're talking about here, it's really important to do them with time resolution. And by that I mean, if you're going to use renewable electricity, you need to make sure that you're meeting the demand for electricity every hour over the typical year. And that's a big deal because it means that there will be some times when you don't have enough renewable electricity, and maybe sometimes when you could produce more, in which case, how do you deal with that? Do you just turn it off, or do you find some way to use it? So what we've been doing in this recent work is looking at the possibilities of when you have excess electricity available from renewable sources, to use that to produce hydrogen in particular. And this is what's called green hydrogen. So what you're doing is you're running an electricity discharge through water to split the water molecule into hydrogen and oxygen. And now you have a carbon-free fuel, if you will, with this hydrogen source. And the first thing you'd want to do is to use the hydrogen source that you're producing here with no carbon residue to replace hydrogen that is currently being used in industry. And in India, one of the major uses of hydrogen is to produce ammonia for nitrogen fertilizer for the agricultural sector. And there also are uses of hydrogen to produce chemicals for the chemical sector, and also uses of hydrogen in the refining business. Okay, so when you take those sources of hydrogen that are being used currently in India, and the same problem goes for China, I might say, what's happening here is that in producing the hydrogen, you're producing the hydrogen from natural gas. So you're taking natural gas and you're splitting it to produce CO2 and hydrogen. And you're actually producing a lot of CO2 from this way of making the hydrogen. And so this is not a very great idea. If you could fix that problem, at least you're on the right trend towards reducing the emissions of CO2. Okay, so what we're saying here is that, look, we have a way of doing this. We're going to do our model study, and we're going to carefully assess how much hydrogen we can produce and at what cost and what it's going to cost us to do this. And the first thing will be to use that hydrogen to replace the current industrial uses of hydrogen. But then we're going to go further. We're going to go further and look at how can we actually use hydrogen as an opportunity to decarbonize some of the industrial sector that I mentioned before, iron and steel, cement, in particular, the chemical industry. So that's a little bit of the background. And again, the way this model works is that we're again going to look at these 5 regions of India, 5 zones, if you will. We're going to have interconnections with the transmission network. We're going to have to do a cost analysis. We're going to ask, what is the minimum cost to meet all the requirements that you see under my assumptions? What is the minimum cost? You're going to do it with the most efficient economic way that you might. And what are you going to pay for that? That's the serious byproduct of this analysis that we're doing. So let me show you a summary of what you get from that. We actually did this using 4 different models. And the model to the left, let's look at the figure to the left. The model to the left of that figure is what we're calling our baseline study. So the baseline study is what capacity do you need to meet the demands that exist in 2050? And then we have a study to the right of this, the third one, is using hydrogen in the power sector. So you can use hydrogen, for example, to produce electricity by either combustion or by a fuel cell under conditions where the electricity supply from the renewables is not adequate. And then finally, on the right-hand side of that figure, you're looking at our estimates of how we could, in fact, decarbonize the industrial sector as well as the power sector and the transportation sector and so on. Now, switching to the right-hand side of this figure, we're giving our estimates of the cost of doing this. And for what I'm calling the baseline situation, where business as usual, if you will, and you see the CO2 emission from this red squares, you see that the baseline is using a very large amount of thermal power, which means coal. And so it's got a big CO2 signature that's even much higher than it was in 2020, because we're having to deal with a larger demand for electricity. The next figure over here is one where we assume that we're going to produce electricity for the 2050 power sector exclusively from renewable sources, wind, solar, hydro, and so on. And you see here, the cost is actually a little higher than the business as usual cost. And you see again the components of this supply. Wind is important, solar is important, storage is important, and so also is a whole variety of the other fossil fuel uses of currently for oil and coal and natural gas. And the other thing I might just comment is that when you think of the Indian economy, India doesn't have a domestic source of oil that is of any consequence. It also doesn't have a domestic source of natural gas that's of any consequence. And so a lot of the domestic energy currently is fueled by coal, and also India does have a large coal reserve, but the coal is pretty dirty coal. And so India actually imports some high quality coal to use in the iron and steel business, coking coal, so-called. So, that's a little bit of background. And so we're trying to sort of deal with that particular issue as we go. And then as you go over to the right hand side of this, this figure, you see that this is where we're going to satisfy the industrial demands as well as all the other sources that I mentioned before, transportation, wind, and solar making a major contribution to that and to domestic situation and so on and so forth. So that's a summary of what we see happening here. And what you see is that there's a major role in what we're doing here for hydrogen in this particular study. Hydrogen that is green hydrogen, hydrogen that is produced essentially from electricity developed from the renewable sources, mostly wind and solar. And so our study is sort of integrating the overall energy economy in these 5 regions with optimized investments in wind and solar and optimized investments in transmission to try to get the minimum cost of meeting all the demands that we have for doing this. And you see here the success of this particular activity is that as we go to these different models, all the way to what we're calling the all model, where you're using a lot of hydrogen, you've actually brought the CO2 level down to effectively 0 under these ideal circumstances. And if you look at the cost of doing that, it's maybe a little bit less than the cost of business as usual. So we believe that there's an economic opportunity here that we need to think about in a serious way. So let me now talk about some other issues here that are relevant. I'm going back to this first chart. When we did this analysis, looking to interpret the transition between the early growth and the later growth, and I made the argument that this is largely the result of negative impact on the climate system due to emissions of sulfur from burning coal. And what happened over this over this time period is that coming out of World War II, and with economic growth both in Europe and in the US, coal was a very, very important part of the energy mix. People were not particularly focused on the fact that it was uncomfortable or unhealthy to be breathing the fumes that came from that coal. And I experienced that as a kid growing up in Northern Ireland, for example. I remember that you go out in the morning with a clean white handkerchief and you come back in the evening and your handkerchief was dirt black. I remember that the smoke coming, most of the heating was from burning coal. I can remember that the chimney sweeps had to come around and get the soot out of your chimney, otherwise you'd have a fire. And they had to do that every week or so. And so you tended to take that for granted as part of progress. And then what happened? What happened in 1950 was there was an inversion that took place in London. And London was also at that stage using coal as a major fuel for heating and cooking in the domestic situation. And with the inversion, the smoky toxic fumes accumulates in the atmosphere for 4 days, and people literally dropped dead in the streets. And that was a really, really serious problem. And a few years earlier, a comparable problem happened in Denora, Pennsylvania. So we were beginning to see that air quality issues could kill people and was very, very bad for the health of the public. So what was the conclusion? The conclusion was that in the case of the UK was to say, okay, we're not going to burn dirty coal. We're going to burn clean coal. And clean coal means coal that will have a smaller emission of particulate matter, less soot. And the same kind of conclusion was reaching in Pennsylvania. Okay, but that doesn't solve the air quality problem, and actually it probably produces more CO2. And then what happens is that towards the end of the 60s, people in Europe and in the United States began to worry about another environmental problem, which was caused by acid rain. And the first indication of acid rain was fish that were being killed in southern parts of Scandinavia. And they figured out that what was really killing the fish was the fact that the rain falling in that area was highly acidic. And we had a similar issue then arising particularly in the northeastern part of the United States, where once again, there were concerns about the acidity of the rain that was falling. And the acid was being produced, in our case here in New England, largely from the Ohio River Valley. And so they were benefiting from having cheap electricity, and we were suffering because it was killing our fish and also destroying our ecosystem. So then what was the conclusion? Well, the conclusion was that, hey, you have to stop the acid rain problem. And so the only way to stop the acid rain problem is to stop the emission of the acidic compounds, sulfur in particular. And so that was what was done politically in the early 70s, both in Europe and in the United States. And so I believe that what you see in this chart is the transition from this hiatus that was driven by the aerosol component to this rising situation. Now, switching to the India situation, India has very serious air pollution. If you look at the record of cities, the 50 largest cities around the world that have serious problems with air pollution, you know, a significant number of those cities actually are located in India. And you know, China is beginning to deal with its issue, not completely successfully, but it's dealing with its issue by in fact trying to cut down on the use of coal and trying to use natural gas, which it mostly has to import as well, as the source of heating in winter to try to cut down on the 2.5 micron air pollution. India hasn't yet begun to really deal with that, and we have to recognize that the pollution problem in India is caused by, number one, is caused by burning dirty coal, both in the power sector and in the industrial sector. And also, and this is really serious, in the agricultural area, India is typically producing 2 crops in some areas, and in the intermediate stage of getting ready to plant the second crop, what do you do with the stubble from the first one? Well, the traditional practice in India has been to burn that. So you're burning that agricultural waste, and in the process producing more damaging pollution and in fact dirty air, contributing to what people have started to talk about as the brown cloud that sort of is sitting over South Asia and was also sitting over China. It seems to have reduced somewhat its presence in China, but it's still a very serious problem in India. So when we think about dealing with the climate issue, I think it's important to recognize that along the way, for the benefit of the Indian economy and the people who live in India, we need to also do some serious work on the pollution issue that is a significant factor as well. So let me, I think I want, let's see, where am I on time? I'll say a little bit more about what we have done in our study here is to focus on the use of wind-generated electricity, solar-generated electricity. We focus on the fact that you can use those sources to produce hydrogen, green hydrogen. You can use that green hydrogen to produce ammonia for the fertilizer sector. You can use that green hydrogen to, in fact, decarbonize the iron and steel industry, and you can use the heat that you can generate from the hydrogen to, in fact, cut down on the emissions from the cement area. And you can also use the hydrogen as an input to the production of chemicals that you need to operate in the environment. So our work is not finished. I've shown you 2 snapshots of what we've done so far, but let me sort of just mention some of the relevant work that we have done in China. situation. We had two papers in the China case that are shown at the bottom of this chart. The first one was published in the Proceedings of the National Academy of Sciences, and the second one was published in Nature. And so what we did in these two studies, in the first of these studies, what we did is we examined the possibility of combining agricultural waste with coal and gasifying the product and using the gases that you produced to produce electricity. And since the gasification process gives you a sort of large CO2 concentration in the production, capturing the CO2 and either burying the CO2 or using it in some other application. And so that was a study that was done. It was a very careful study, and it's not a simple thing to do. You have to run a very complicated model to see what's the best way to do this. The model it was developed in the US. It's called Aspen Plus. And so this particular author, this particular study using Aspen Plus led to the conclusion that with a mixture of, I think it was 35% renewables and 65% coal, the CO2 that you captured would be carbon neutral. In other words, so long as you didn't allow the CO2 to get out, you had in fact cut down the emission of CO2 to the environment. And if you use more biofuel, so that you pay some price to do that, you can actually get to the point of having this technology be carbon negative. In other words, you are capturing CO2 from the coal input, but given the fact that you have this large source from the agricultural biomass, you're actually the net carbon is zero, is actually negative, and that's a really important part of that particular study. This study has got and continues to get a fair amount of attention. Now, the second one is an interesting version of this. Again, it's using biomass, using agricultural waste in the China context with real information about how much is available. And what it's doing is using the biomass to produce biochar in particular, and of course also producing electricity along the way, and then using the biochar as a way to add the biochar to agricultural systems. And the analysis suggests that once again, if you do this carefully, you can add the biochar to regions, agricultural regions, where the carbon in the biochar will be protected for 100 years if you pick the right environment. So that was an important part of that particular study. And again, it's not an easy thing to do because you want to be careful that you are using serious models of how this system works. And again, the use of this code called Aspen Plus is a very important part of it, because the intuitive decisions that you might make are often wrong. I mean, the question is, what's the best temperature to do the pyrolysis, and what are the byproducts of the pyrolysis system at higher temperatures, moderate temperatures, and lower temperatures? What's the optimal way to operate the system? And so that's been a part of the study that I think is relevant to what we're doing here with India. So what I wanted to do is to say that, look, China has a significant agricultural system. The agricultural system has some of the same properties that India has. And rather than burning the organic waste, if you can collect it efficiently and transport it to central places, you can use it as a way to cut down on CO2 emissions, and also as a way of cutting down on air pollution. And so that is an important opportunity. And I think for India, it's important to recognize that the potential source of agricultural waste in India is probably larger than it is in China. And in addition to that, you have the problem of municipal waste in India, which is a serious problem, because once again, there's not a lot of land to build landfill places to store that municipal waste. And once again, the tendency is to say, okay, the easy way out of this is to just burn this stuff. And burning the stuff, you're killing people from the air pollution, and you're also passing up a major opportunity to make a difference in the climate area. So that covers some of a fair amount of what I wanted to talk about. And you know, I think what India is trying to do is to make a difference along the lines that Modi's commitments were, but in some sense, it's doing it in a fashion that needs critical input to make sure that, you know, the problems are that we do it the best possible way. So one of the major announcements very recently in India was that the government has announced a program to use coal and to gasify the coal and to produce methanol and ethanol for the transportation sector. And okay, that sounds laudable, but the problem is that the study and all the literature that we've had an opportunity to read doesn't recognize or doesn't talk about the fact that the amount of CO2 that you produce in doing that is enormous. And unless you have a plan to capture all that CO2 and do something with it, then, you know, that plan needs to be modified to a significant extent. Part of the reason given by the Indian government in this plan was the opportunity to cut down on the need to import oil and the economic implications of the amount of money that's been spent to import that oil. And so if you can now fuel the transportation sector with coal, Indian coal, effectively, then at least you have made a difference to the economics of the energy system in terms of cutting down on the inputs. Final point I want to make is that we are also looking at. Let me flip to one of the charts I wanted to show. We're also looking hard at the opportunity to use ammonia as a fuel, and you know, this got some publicity in a paper published by the Royal Society. So a couple of years ago, we did a study looking at the opportunities to produce hydrogen from offshore wind in China, and to transport that hydrogen product to Japan, where Japan has a policy objective of having hydrogen a major input to its economy in 2040. Okay, so in doing that study, one of the issues we had to deal with was, how do you get the hydrogen that you produce from electrolysis, from renewable energy? How do you get the hydrogen to the market? How do you get it to Japan in the case that we were studying? And so one of the possible ways of doing it is you turn the hydrogen into ammonia, and you transport the ammonia, and the ammonia is easy to transport because it's a liquid, and you can transport it with existing shipping. And when you get the ammonia to Japan, you have two options. You can turn the ammonia back into hydrogen, or you can use the ammonia as a fuel to substitute for coal in particular. You can add ammonia to coal and burn the ammonia coal residue and cut down on the CO2 emissions, because the ammonia has no CO2 component. And so, you know, as you can see here, looking at to the right, the expanded uses that we're contemplating is number one is to retrofit marine. One of the other issues we're facing globally is that a significant amount of CO2 emissions is actually coming from the marine situation, from the shipping of goods in big tankers and in big transport vehicles, and it's using dirty bunker fuel and producing a lot of CO2, and that's a problem. Well, one of the things what we looked at here is you could retrofit the marine engines to run on ammonia, and now you have at least cut down on the CO2 emissions, and that's a step in the way. And there is actually a study by this corporation man that has looked at a demonstration project to do that. And, you know, as I comment here, ammonia motors and engines have been developed for a long, long time. Then in terms of electricity generation, co-firing ammonia with coal in coal-fired power plants, blending share has been demonstrated to work effectively in Japan in 2021. And there's also the possibility of direct combustion turbines and fuel cells, and other particular sources that are involved. Let me sort of thank you here and pause and be delighted and happy to answer any questions or to have a conversation about some of these issues.
Okay, Mike, thank you very much. This covered a lot of territory and a lot of food for thought on many, many issues. I talk to Mike every day, so I'm not going to ask any questions. But please raise your hand electronically if you have a question. Okay, Jim, I see you want to ask a question, but I'm going to first ask Hitesh.
Mike, that is a very comprehensive and illuminative look. Thank you very much. I think you've laid out the issues and avenues very clearly. You touched on the costs, and I wanted to ask more about that. I've been speaking with a variety of government officials in India, Bangladesh, Sri Lanka, Pakistan over the last few months. And essentially, everyone feels that the expense, the investment needed to transform the infrastructure is in the trillions.
Yeah.
And that without talking about trillions of dollars, nothing is real. Every number, every goal you put is unreal. And of course, India's GDP is about 2.5 trillion, but multiple trillions are not easily to be got at. So how do we resolve that issue? I mean, something the European Union, I know, is thinking about quite seriously also and has set aside funding. But is there a way to address this concern?
I think that's a very, very important question, a very important issue. There's an interesting study that was done by McKinsey people for Europe, actually. And the conclusion was that making this transition to zero carbon would, in fact, in the long run, not negatively impact the GDP of the European community. And more interesting in the study, the conclusion was that poorer people would actually be better off in the long run with this investment. And part of the reason for that, it was that, in fact, in order to make this transition, you need to have a very significant, as you point out, a very significant capital investment. But once you have the capital investment in place, you're not paying for the wind and you're not paying for the solar. And at the moment you're paying for natural gas, you're paying for, so the fuel is effectively free. And so the argument is that in the long run, this is actually good for economies. But it's a serious issue, and working in its favor is the fact that the cost for some of these renewable fuels is coming down very significantly, wind and solar in particular. And so that's a step in the right direction, but it is still a pretty serious issue. And what we have done in our work so far is we sort of have focused on endpoints. Say, okay, let's imagine that we get to 2050 in this particular situation, satisfying all those demands. We need to do something more than that. We need to see, how do you actually get there? We need to do a dynamic analysis, because that's where the rubber hits the road, as they say, because the dynamic analysis is going to raise the issues of capital investment, when you're going to do it, when you can do it, and what are the challenges that you face. I mean, one of the things I find interesting about what's been happening very recently in China is that the Chinese government had these very ambitious plans to decarbonize very quickly to 2030. Okay, and then they had a problem. The problem last year, the problem they had was that, in fact, suddenly there was a shortage of electricity. There were brownouts. And the brownouts were attributed to the fact that there was a shortfall in the supply of coal. A lot of coal-fired power plants were essentially turning off. And why were they doing that? Well, they were doing that because the price of coal last year globally rose. And if you are running a utility in China, in this particular case, and the price of electricity that you're going to get is sort of fixed by the government, and if the coal that you have to buy or to supply is going to cost the electricity to be more expensive than what you're going to get for, then the obvious thing to do is turn off the coal-fired power plant. And so you make some excuse to the government and you say, okay, we're turning it off because we're going to do a refurbishment and so on and so forth. Okay, so, and then you have this serious political problem, because on the one hand, the central government in China wants to decarbonize, but they also want to make sure that people are getting a steady supply of electricity. So what they just recently announced, which is very interesting, is that they're going to continue to invest in coal-fired power plants, but the expectation is they're not going to use them unless they have to use them. So you sort of pay the cost of the investment and so-called capacity credit, and then you use it when you have a shortfall. So the question you raise is a serious one, and it needs serious attention in terms of the economics of making the transition. There's no doubt in my mind, though, that if you can suffer the early pain, the end product is actually pretty good. And in the case of India, you're going to cut down on the expense of importing that oil and the expense of importing the natural gas. And so you're going to become energy more independent. And so there are advantages, but it's a serious issue. Which the last comment I want to make is that one of the reasons I think it's very important here at Harvard that we build this community, that it includes not just the physical sciences, but also includes the people who understand the politics and the economics of the countries that we're trying to deal with, and the social aspects. I mean, we need to. That's why we need to have a close relationship with your institution and with other institutions around Harvard. We need to build a Harvard community, and we also need to think about ways of bringing Indian scholars into this mix. I mean, one of the great successes that we've had in our China project is that Chris mentioned the number of alumni. What was it, 200, Chris, or something?
Yeah, 200.
Over the years, these are Chinese scholars who come to work here at Harvard and then gone back to China, and now occupy academic positions and government positions in China. I would love to think of us doing something similar in the Indian context. And I mentioned in the beginning this China Council, which was set up after the Rio summit. The China Council was actually funded initially by the Canadian government. And the commitment that they made is that if China agrees to have this China Council, which would have equal numbers of Chinese experts and foreign experts, and would have the opportunity to talk directly to the highest levels of the Chinese government, then Canada would pay the bill. And that's been a very, very successful program. I would love to see something like that happen with India as well.
I think you're pointing us to all the right directions. I see that Rob Stowe from the Kennedy School, who's also an expert on the topic, is with us and a partner to the McElroy. I think it is, there are questions about, are there policy changes that can incentivize to private investment, for example, to solve some of this problem? But at the end of the day, it's also about political pressure. And as you pointed out, in your own native Ireland, you had got used to a certain amount of smoke. I'm thinking of, I think it's T.S. Eliot's The Love Song of Alfred Prufrock. It has this beautiful line, the yellow smoke that rubs its back upon the window panes, where the smoke was so familiar, it was almost like a cat in the metaphor, But once people wake up to how dangerous it is, things begin to change. In any case, I'll let others talk now. Thank
you.
Yeah, we need to get a couple more questions in here. I want to go with Abhishek Malhotra.
Yes, thanks a lot, Professor McElroy, for the presentation. It really does a great job of illustrating the endpoint that we want to get to, but you're right, it does raise a lot of questions about how to get there, which includes all sort of questions related to how do you design institutions, markets, what are the distributional effects, how do you balance decarbonization with costs and costs with other policy goals in the energy sector. But since you focused on costs, I'll keep my question also focused on costs. I'm wondering about what are, in your high renewable penetration scenarios, what are the balancing options that have been modeled? What is the contribution to the overall costs? And also, what is the contribution of to the overall cost of adaptation? So that includes industry as well as transport, because electrification will also require capital investments on the end use side as well, right? So have these been taken into account? And just could you talk a little bit more about that?
Yeah, it's again a very good question. So what we have done here is this is you know, the shortcoming of what we have done so far is we pick the target year in the future. We want to see what's the cost of operating that new system, and what we really need to do is to do the dynamic analysis of how you get to that particular situation in a realistic economic path. And so that's a challenge that we need to do. And the other thing is that, look, the particular model that we have published with this emphasis on wind and solar in particular, we don't pretend that that's the only way in which you can get to 2050. We would say that, in fact, we need to have a better analysis of what you can do with the biofuel issue in particular, but we need to do that also realistically. I mean, there's been a tendency to assume that you know, since you have all that wasted biofuel, that you can do all kinds of things with it. And we've talked about just 2 studies that we did with China, but there's a lot more work to do in that particular area. In terms of how this actually works eventually, to the extent that India is currently buying the oil that it needs from uncertain sources and the natural gas, it doesn't have the supplies. The opportunity to do things domestically is potentially good for energy security, and that's a good thing for India and for other countries. But in terms of economic development, you know, if I'm capturing that CO2 from the bio combination of the biosource and the coal source that I mentioned in these 2 papers, if I have essentially a supply of effectively pure CO2, remember that I can take that pure CO2 and I can react it with hydrogen produced from this green mechanism. And now I can develop a whole new industrial product. I can produce the transport fuels from the combination of CO2 and hydrogen that allow me to replace the current uses of coal and oil. So yes, there are costs, but there are also incredible opportunities. And in India has a creative industrial sector, it seems to me. I know a little bit about Tata, for example, as a major industrial powerhouse. And I think that the opportunity to interact with industrial leaders as well as academic leaders in India, we're going to learn more by working together, including dealing with these economic issues. But thank you for the question.
Okay, Rob, you were patiently holding your hand up and your name was invoked. So Rob Stowe.
So yeah, Mike, I just was wondering how you're defining cost. You have referred to it variously as having operating components and capital components, but could you define what you mean in this model?
Okay, the way we did it, Rob, in this particular model is that to the extent that the future also continues to have a demand for thermal power, for coal-fired electricity, then mostly that is going to be the capital cost of that coal and the operational cost. we're going to assume in our model, we're assuming that instead that you don't have to build more coal-fired power plants. You essentially have them and you maintain them, and so it's the operational cost that's important. Now, in terms of the wind and solar, the way we do this is that we think of what the capital cost is to install a gigawatt of wind or a gigawatt of solar, and then we imagine amortizing the cost over the lifetime of the investment, with an assumption about what the interest rate is. And so what we're doing in the costs, the costs are including the cost of capital and projecting the amortization of that cost, the return on the investment, if you will.
So may I just ask a quick follow-up? So you're comparing the capital cost amortized for wind and solar to purely operating cost of existing coal, with the assumption that there's not going to be any more built after a certain point.
That's correct. Yeah.
And also assuming it's fully amortized.
Yes. Yeah, that's
Okay.
correct.
All right, thanks.
But you know, also, I mean, again, you're raising an important point here. I suspect that as we try to do in this next stage, the dynamic analysis, we're going to have some surprises, because we're going to find our investments in wind and solar don't meet the requirements for electricity generation in 5 years' time or 10 years' time. And we need to keep the coal-fired power plants operational. And that's going to affect the costs of the entire system. So the dynamic analysis is going to be really, really important. And I think what we're seeing in China is the government finally sort of appreciating that, gee, we forgot about the fact that you might have to absolutely have those coal-fired power plants available to use, even if you're sitting there idle for most of the time. These are tough problems.
Okay, I think we're going to have two more questions. One, I'm going to read from the chat. It's from, and then we'll end with you, Prem, because we owe it to you for getting up in the middle of the night to attend this seminar. But the first one is from Rambir Parmar. He says, can you please comment upon where does India stand as far as coal gasification as a cleaner fuel?
Thank you.
Okay, I think that's interesting. The way I have read the recent policy announcement is that India is going to encourage, they're going to investigate a number of coal mines for the quality of their coal and for the opportunities for that coal to be gasified productively. So the initial investment is going to be to do an inventory of what the possibilities are of producing of doing that gasification. And you know, in doing the gasification, the idea, at least as I read the policy, is largely directed at the transportation sector. And it's directed at producing methanol, which you can certainly do from the gasification process, and potentially ethanol, and perhaps some other chemicals. And that's the way I read the current Indian policy. What struck me as an omission was the lack of discussion, but maybe I'm simply not getting it. Lack of discussion about what you do with the CO2, large CO2 product that you get from doing that. And I think that I also I think that the plan is to do a careful analysis of the economics of this particular process as well. I mean, people can say, okay, well, the coal's cheap, and so we can do this. But you have to really understand what it's going to cost to do that. And I think the Indian government plan is to, in fact, investigate that to the point of being able to define how economically viable that particular source really is. I might say that in the book I wrote a couple of years ago, when I near the last chapter, when I started looking at some of these opportunities, I made a point that for decarbonizing some of the difficult sectors to decarbonize, let's think, for example, about jet fuel. That one good thing that you could do is to use biofuel to produce jet fuel. But when you looked at the economics of how you do that, you had to do that with a combination of coal, because if you tried to just do it with biomass, it was incredibly expensive to do it for even a small scale. But the combination of using coal and biomass to decarbonate, to produce a jet fuel was in fact fairly attractive. And I might say our colleague Dan Schrag gets some credit for an interesting paper that in fact defined that particular issue. And I simply picked that up in my last chapter. Thank you.
Okay.
Now my friend Prem.
Prem.
He's going to sleep.
You have to unmute, Prem.
Done. Thank you, Chris. There are so many points that Mike's long talk has given us that I just don't know where to begin, but there are a couple of things I do want to say. I think that there is a general issue that all of us have got to face before even we start talking about the specific technologies and how they'll be used and how costly or otherwise they would be, which is that there is the three areas that we need to have solutions for are well known: consumer consumption, industry, and transport. Now, in all of these, we have the technologies are known as far back as the Copenhagen summit. The scientists telling the summit people that look, we know the technologies. We have not been able to go for beyond that, because one is that there is no understanding, particularly if you take China and India, that the purposes of the shift are different for the industrialized countries, the rich countries, and for the developing countries. For the industrialized countries, the purpose is minimal. It is to move out of one energy source into another while disturbing the rest of the economy as little as possible. As it is, your growth rate is about 1.6% average against 4 to 5% or even more for the developing countries as a whole. So, the growth is the problem of reconciling growth with shift of energy is not there. In our cases, there are a whole, not just growth, but a whole series of associated problems have to be also seen, and we have to choose only those technologies which will meet the maximum number of these other associated goals. I won't go any further than this. I want to just mention the 5 that are critically important and that have to be borne in mind, and which give you, once you bring them in fully, give you a different combination of the technologies that we have in front of us today. These 5 are, first of all, unemployment. Huge in India. Over 100 million people have even stopped looking for work between the ages of 16 and 59, just stopped looking for work. The second is growing income inequalities, which is a worldwide problem, but has become a particularly serious problem recently in the developing countries and particularly in India. The third is uncontrolled urbanization, with all the problems that we discussed, including the problems of air pollution, water pollution, disposal of urban solid waste. What do we do with plastics and so on? The fourth is, as I said, air and water pollution. And the last one is that actually capital intensity and complexity should be minimized, particularly complexity. And one of the problems that we are not really facing so far, and which Mike touched upon just at the end about saying that we may have to keep coal going for much longer than we realize, is the problem of intermittency of wind and solar energy. And this, there are, of course, the simplest problem in theory is the concentrating solar power being the backup of for solar photovoltaic, but everyone raises the issue of costs. So I'll end with the issue of costs. There are private costs, which is the cost to the investor, and there are social costs, which is the cost to the country, to groups of people within the country, and ultimately to the world. And you know what I'm talking about. And there's no way that a system, a market system, which is based upon private costs and returns alone, can ever give you solutions to what to choose on the basis of social costs. I'll stop there. I think that once you bring in social costs, you get a whole different picture of the relative importance of the technologies that we all know about. Thank you, Chris. Thank you, Mike. It was great to hear you.
Thank you, Prem. And you know what I would say is that you're absolutely right. We do have to consider the social costs, and you know it's easy for us sitting in a nice comfortable place in Cambridge to say, okay, it's really important that the air quality experienced by people in the northern part of India should be better than it is. Okay, great. And we can offer the obvious ways in which you could do that. But then you have to think about it, as you've been educating us very importantly, you have to think about, as you make that transition, who's going to suffer from that? I mean, what's the impact on what you do? And clearly, I mean, you have been bringing up some very important points about the need to address particularly poverty in the rural areas, and to prevent the sort of the forced migration of people into these mega cities, and all of the problems that go with that: poor housing, possibly crime, and water quality problems, and so on. And so, if you can provide employment for those young people, and that's really critical. India has a young population; it's growing, a young population, and we have to be, whatever we do, we have to make sure that we're taking care of their needs, and employment needs is really an important thing. And you know, you've been talking about the possibility of using local agricultural waste and building essentially an industry around that pays the people to. And I think we need to keep talking about that. We can also talk about some other issues that might provide the same objective. So, for example, having in a rural village, I mean, that's the other problem that I didn't mention, but you know it very well. The large fraction of the Indian population that doesn't have access to electricity is really incredible. And so that inhibits development in a major way. So the Indian government appropriately is trying to target 100% electrification for its population by a relatively immediate time scale. But you know, and we're talking about trying to do it with essentially utility scale production and transmission over the grid. But I think you and I need to have a conversation also about in a small village, would it not make sense to have a sort of a small central PV system that is producing electricity that is available for the residents of that particular community, and allowing them the opportunity to do things that they can't do at the moment? You've also made the point that electrification is very important in terms of storage of food stock that might otherwise be wasted. And you also made the point to me, which I think is a very interesting point, that Indian farmers are often selling their crops at ridiculous prices because they can't store them. So the market can just gobble them up for whatever the market wants to pay. So yep, you're raising lots of points, and I'm really enthusiastic, looking forward to continuing our book project, which I think is going to be fun.
Okay.
Also, I think you need to go to sleep. You're too old to be up this late.
We're
Mike,
at.
I slept for 2 hours this afternoon in order to be able to stay awake. But thank you for worrying, and thank you, Chris.
Okay.
We'll see you in a few weeks.
We're at 4:30. We've exhausted our time. We want to thank everybody for participating. And thank you for the Mittal Center for co-sponsoring with the China project on this, and Tesh, thank you for your participation. Everybody's questions and rapt attention is appreciated. And finally, Professor McElroy, thank you for an outstanding talk.
Thank you, Chris.